All right, I think we are live. Just wait until the stream kicks in on my computer, make sure everything is working properly, and then we get underway. Okay, I think we can do this full screen. Give myself a little bit more room to work with. Good, I can see myself. Looks like we're okay. We're working. Adjust my webcam a little. There we go. All right, I got 12 online. Hopefully we're good to go. Welcome everyone. I'll say hi in the chat. We are finally at the last class. Believe me, I'm more relieved than you are. This has been an interesting challenge doing this from home. Okay, let's get underway. I hope everyone can hear me all right. We've got functions of several variables to talk about. This is the last thing we need to do to be done. All right. Uh-oh. And I can't find quiz 16. Did I forget to assign it to y'all? Let me, here, I got my desktop open. I bet I messed up. And I find it hilarious that this is the first anyone's complained about it. Okay, homework sets editor. Where is it? Huh. I swear I made it. It's not there. Okay, I apologize for that. There it is. Okay. All right, Hannah. I don't know what happened to quiz 16. What did I do? Did I put it in 1410? Maybe I put it in the wrong. No. Yeah, I got no idea. I know I did it. I know I set it up. I remember doing it. Did I give it the wrong name? 13, 14. Yeah. I guess there's no quiz. All right. All right. Can everyone manage if you don't get a last quiz? Let me know. If you're really counting on having one more quiz, I can set you up with one. If you can live without it, well, I don't know where the hell I put it. Yeah. Okay. It's been a rough go. Let's move on. Let's talk surfaces. So there's a couple of different kinds of surfaces that you encounter when you're starting out with functions of several variables. Graphs and level sets. We saw some examples of this last time. So a typical example of a graph might be something like, say, z is equal to x squared plus y squared. So this is a circular paraboloid. So you kind of draw a parabola. That parabola is basically like your trace in the YZ plane. And then you say, okay, well, it's a parabola with sort of circular traces in the planes parallel to the Z direction. So you get something that looks like that. Okay. And it is a graph. It's a graph in the sense that for every point in the XY plane, right, there's a corresponding point on the surface of the form x, y, and z, where z is equal to x squared plus y squared. Okay. So you'll have surfaces that can be rendered as graphs, and you also have ones that can be rendered as level sets. So an example is a level set might be something like this. So this would be hyperboloid of one sheet. So what that hyperboloid looks like is in the YZ plane, you have a hyperbola. But if you cut it in a plane that's parallel to the XY plane, you get a circle. So this would be this is called a hyperboloid of one sheet. There are also hyperboloids of two sheets. The one-sheeted hyperboloids, they look kind of like like the old cooling tower at a nuclear power plant, something like that. In fact, that's exactly what those are shaped like. They're shaped like hyperboloids. That's not a very good drawing of a hyperboloid. But you get some idea of what they look like. So it's kind of the same thing, and we see this already even in in 2 dimensions, right? Graphs where we write y as a function of x versus other curves that are given as implicit equations like circles and hyperbolas and ellipses, right? So you get that same kind of 2 different ways of looking at objects in 3 dimensions, just the same as you do in 2 dimensions. You can also do parametric surfaces, but that's definitely something you're not going to encounter until you're well into your 3rd or possibly 4th calculus course. You can do parametric surfaces just like we can do parametric curves, right? And of course you can do calculus with all these things. And so one of the things you do, just like you can do implicit differentiation, right, in 2 variables, you can do implicit differentiation in 3 variables, where you say, okay, this hyperboloid of one sheet, it's not a graph. It fails the vertical line test. If you want to, you can still think in terms of vertical line test if you want. It's not a graph, but locally it's a graph, and so you can still do like implicit differentiation. We are not going to do implicit differentiation in this course because before you can talk about implicit differentiation, you got to talk about chain rule for functions of several variables. Chain rule for several variables is a lot more involved than it is in one variable, but it's something you get the hang of. But it's definitely not a Calc 2 thing. It's a Calc 3 thing. Okay. One of the things you can do, again, if you're having trouble visualizing these things, is you get yourself a good plotting utility. CalcPlot 3D is a pretty good one. I find I like CalcPlot 3D a lot. This was supposed to be linked, but it's not linked. It's okay. Go have a look at CalcPlot 3D. It actually has a bunch of built-in examples, and they're interactive. And I also want to remind everyone that the graphics in the textbook, are also interactive. Actually, I'll give you in the chat. I'll give you the link for CalcPlot, just so you can have a look at that. Okay, copy the link. Let me throw that over on the. Oh, of course. That's not how I want to do my link. Grab the link. It's made the mistake of grabbing the Google search link instead of the actual link. There's the link for CalcPlot 3D. And again, have a look in the textbook, because all the 3D graphics in the textbook, if you're using the HTML version, all the 3D graphics in the textbook are rendered in WebGL. It's interactive and they're very easy to play around with. You can grab them with your mouse and drag to rotate. Actually, even the PDF, if you're using the PDF version of the textbook, if you open it in Acrobat, it won't work in lightweight readers. But if you're reading the textbook in Acrobat Reader, you can click to activate a lot of the 3D graphics and you can play around with them. So use interactive graphing software when you're getting the hang of 3D things, because they're tough to visualize first time around. It's tough to visualize them. Okay. All right. So functions of several variables. So the first thing I want to emphasize is that functions of more than one variable are still functions, right? I mean, if you think about the, what's the basic definition of a function? And you see, if you've done, say, Math 2000 or something like that, you've seen this sort of thing, right? A function is just something, it's a relationship between sets, right? A function is something that takes, inputs from one set the domain and gives you outputs, right? And so it doesn't matter whether you're talking about a function of one variable, two variables, three variables, whatever, right? That number of variables, all that is just saying, well, what is the dimension of the domain, right? How many variables do you need to describe points in the domain? But a function is a function is a function. There's an input and there's an output. And we just happen to be now looking at cases where the input is an element of R2 rather than an element of R, right? So the two variables are because you need two coordinates to describe points in R2. And of course, that is going to have an effect on how we do calculus, but I want to emphasize that functions are still functions, right? So if I write down something like, f of x, y is like this one that we just graphed, x squared plus y squared, right? It's still the case that you get a unique output for every input. So if I do something like, what is f of 1, 3? I say, well, f of 1, 3 is 1 squared plus 3 squared, which is 10, right? You can plug in the numbers, right? If I wanted to do something like f of, I don't know, a plus b, a minus b, for some reason I could do that. A squared, I would get, a plus b squared, a minus b squared, so I would get a squared plus 2ab plus b squared, plus a squared minus 2ab plus b squared, so I would get 2a squared plus 2b squared. I don't know. What are a and b? I don't know. There's some numbers. We can plug them in. We can see what happens, right? So you can do things like that. You can play around. So there's lots of things we can do, right? And of course we can use any familiar functions that we have to invent functions of several variables. So I can say, I want g of x, y to be, like the square root of x plus, I don't know, e to the sine of x times y or something like that. We can do that sort of thing, right? So the point is, it's really any kind of formula that you can think to write down involving two variables is going to define a function of two variables, right? That's pretty much all there is to it. And there's no real reason that you have to stop at two variables. You can go to 3 or 4 or however many variables you want to use. The main reason why we stick to two variables starting out is we can still visualize graphs for functions of two variables, right? Once you get to a function of 3 variables, the graph would be something that lives in 4 dimensions. And drawing things in 4 dimensions is hard, right? I can't picture 4 dimensions. If I could do a function of 20 variables, but then the graph lives in some 21-dimensional space. I have no idea what that looks like, right? The math works out. The math works just fine. You can still do all the algebra. You can still do all the calculus. Doesn't matter how many variables you use. But actually kind of picturing things, that's where it gets tricky. So we live with it. Okay. Here are some more examples. So we just want to compute values of functions at points. We can also talk about domain and range, right? I think I gave you some web work problems like this. So for the first one, if I wanted to do f of 0, 0, well, that's going to be 0 squared minus 0 squared. I just get 0, right? And this is for 1. If I want to do f of 1, 2, well, that's 1 squared minus 2 squared, so 1 minus 4, I get minus 3. F of 3 minus 2, 3 squared, subtract minus 2 squared, so 9 minus 4, I get 5, right? So this is easy, relatively speaking. Domain. What is the domain for this function? Well, the domain is all of R2. We take the same convention for functions of 2 variables that we do for functions of 1 variable. which is that the domain should just be the largest set of values that make sense, right? And this first function is essentially polynomial, right? You're squaring two numbers and subtracting them. That's going to work for any choice of numbers that you want, right? Yeah. Okay. So we can do things like that. Uh-oh, I got a question. Somebody's confused. Confused about what? Wait and see. What is a derivative? That's coming. We'll talk about derivatives. We'll talk about derivatives. We're not at derivatives yet. Derivatives are coming. Right now, we're just talking about like how do you describe a function, right? How do you plug numbers in, describe domain, range, things like that? We'll get to derivatives. Derivatives are coming. What is a polynomial? Okay. Is this somebody in our class? We know what polynomials are, right? Polynomials are things that you get by taking powers of variables, right? We know what a polynomial in one variable looks like, right? A(n) x to the n, a(n) minus 1, x to the n minus 1, so on, a1x, constant term. So we can do polynomials in two variables as well. We can have a constant, right? We could have maybe a1x, we could have a a2y, we can have a3x squared, we have a cross term x times y, y squared, and so on, right? Anything that you can get as, yeah, you're late on April Fools. Okay, let's get back to work. What about range? So range is something you have to think a little bit harder on, right? For a function of two variables especially. How do you think about range? What are all the possible output values? Well, the easiest way to think about range for this one is to say, well, look, if I just put y equal to 0, right? If I just look at, f of xy equals x squared and I ignore the other part, I can get every positive number, right? X squared has range from 0 to infinity. If I put x equal to 0 and I just look at the minus y squared part, I can get all the negative numbers, right? So the range for this thing is actually every real number, right? You can get every possible real number for that one. Okay. All right. Let's keep going. I'm only going to keep half an eye on that chat now. Second one, e to the minus x squared plus y squared. So for this one, well, again, we can plug in numbers, right? Like e to the 0 squared plus 0 squared is just 1. If I wanted to do, what is f of, say, 1, 2, that's going to be e to the minus 5, etc. I'm not going to plug in too many of them. It's kind of boring. Actually, this one is a cool one to sketch. If you sketch this thing, you get this kind of like hilltop thing going on. That 1 at the origin is actually the maximum value for this, and you get kind of a, it's like a Gaussian, but it's a Gaussian in every direction. So you get this sort of hilltop thing going on for the graph. And so if you think about what is the range for the second one, well, again, the domain for the second one is, again, all of R2. We can plug any point we want in. The range for this one is this interval from 0 to 1, right? Because the function is given by this decaying exponential, right? Exponential function is never negative and it's never 0. But because it's a decaying exponential, the largest value that you can get out of there, right? Because the exponent is never negative. X squared plus y squared is bigger than or equal to 0, right? So the maximum is going to happen when x squared plus y squared is equal to 0, and you get e to the 0, which is 1. Okay. The last one, number 3. The only thing I want to do with 3, I'm going to let you plug in the points. And in fact, f of 0, 0 is undefined, right? So is f of 3 minus 2. Yeah, I'm just going to ignore that. So the main thing I want to point out for the third one is that the domain is we need x times y to be bigger than 0. And there are two ways to get x, y bigger than 0. We can have x bigger than 0 and y bigger than 0, which is like quadrant 1, or we can have x and y both negative, which is quadrant 2, or quadrant 3, right? So you can have first quadrant, you can have third quadrant. And the other thing, though, you do want to be careful about is you might be kind of tempted with this third one to say, well, hey, can I write that as like the natural log of x plus the natural log of y? You can in quadrant 1, right? But if x and y are both negative, then that property of logarithms doesn't work, because if x is negative and y is negative, then log x, log y those are not defined. But if you're in the first quadrant, you can get away with that sort of thing. Okay. All right. Ready to move on? Let's move on. Okay. So then we can get into things like, how do you graph functions of two variables, right? Visualizing, kind of tricky. One of the things that you typically do is you look at these traces. So remember that basically the way you get traces is you kind of intersect. You intersect with planes, and the best ones to do are, see what happens when you put x equal to 0 and look at the yz plane. Put y equal to 0, see what happens in the xz plane. Or you can look at the traces that you get when you set z equal to a constant. Okay, or I guess I called it k. I'll stick to k, right? So those traces that you get when z is a constant, these are called level curves, right? So if I'm plotting, say, that first example there, x minus y squared, I can say, okay, well, what do I get if I'm doing, say, z is equal to 0, right? So z equals 0, I just get y squared is equal to x. So that's actually, I get that, y squared is equal to x, right? That's the z is equal to 0 trace. But then if I do other values for z, right? If I do, like, what's the z equals 1 trace? I just get, if I put z equal to 1, I get x minus y squared. So now I get that, I get y squared is equal to x minus 1. Okay? And that's still a parabola opening out. It's just been shifted, right? And so you can play these games, right? So y would be square root of x minus 1. And so you get kind of what you should get actually is you get a line like that. So that's the y equals 0 trace, right? The y equals 0 trace is just the line z is equal to x. And then coming off of that line, you have these parabolas. And so this gives you some idea, maybe not a great idea, but some idea of what that thing looks like, right? So you get this sort of parabolic cylinder, but it's at a bit of a slant. Again, it's not art class. That's a really bad drawing, but we get the idea, right? The next one here, this is going to be one of these elliptic paraboloids. So you get something like this, opening upward. The sine x cos y, I'll let you put that one into the graphing utility and see what you get. It's kind of a fun one. It's an interesting one to try. And what you can think about for that one is, So z has to be kind of between -1 and 1 because sine x and cos x are between -1 and 1. And you can look at what happens if you kind of hold x constant or you hold y constant, right? So if you hold x constant, you get sort of sine waves in the y direction. But if you hold y constant, you get sine waves going this way. And so you actually get this kind of, it's just a whole bunch of bumps. So you get this kind of really hilly field when you try to plot it. And you should ask the computer to plot it because it'll do a much better job. So you can play this game, right? You try to sort of set variables equal to constants and you plot the corresponding curves. And sometimes they look terrible, but at least it gives you some very rough idea of what things look like if you need to know what they look like. Okay. All right. So level curves are these curves which are actually kind of like on the surface. So these are like if you ask the computer to plot a surface, it's always going to show you these grid lines when it plots the surface. Those grid lines are level curves. The grid lines are typically level curves corresponding to just holding one of the variables equal to a constant while you vary the other two. You'll also see these so-called contour plots, right? So a contour plot, if I was doing like that z is equal to x minus y squared, the contour plots are actually plots in the xy plane. And so you do, so here's x, here's y. And so you'd say, okay, well, here's my z is equal to 0 plot. And here's my z is equal to 1 plot. And here's my z is equal to 2 plot, and so on. And you just draw all those curves in the plane. So contour plots, these are kind of like, you know, they're like topographical maps is kind of what you want to think of here. You know, so you know when you're like mapping mountainous regions and you kind of what you're plotting there is you're plotting kind of the curves of constant altitude, right? It's holding z constant, so it's those constant altitude curves, and that gives you some idea of what things look like, right? If you're doing say z is equal to 4x squared plus y squared, and you try to plot that one. So then for each constant value of z, what you're getting is you're getting an ellipse. So you're going to get something that, you know, looks like that. Right, so you can draw those curves in the plane. If you do the one for that last one, actually the contour plot for that sine x cos y one, that's kind of a fun one to graph as well. I'm going to leave it to the computer. Okay. This is the only thing I'm going to say about limits. I'm not going to test you on limits at all. Limits are not super important. Okay. Limits are important. They're not important for 2565. And one of the reasons is that limits are actually really difficult to get a handle on, right? And the reason is that, you know, if you think about one variable calculus, right, we spend all this time in one variable doing things like, okay, we got to check to see if the left-hand limit is equal to the right-hand limit, right? If the left and right-hand limits are equal, then the limit exists. But the problem is once you get to, you know, more than one variable, like you're trying to find the limit as you approach some point, right? There's some point a, b, and you're looking at the values of function where xy is close to a, b. And you say, well, what does it mean to be close to that point, right? When we see, you know, remember that when we're saying, we always say like x approaches a, right? When we're talking about a limit, we're saying x approaches a, we're saying, well, we're looking at values of x that are really close. But now really close would mean, you know, anywhere inside some sufficiently small disk. And I can enter that disk from any direction. I can come at that point from any direction. And in order for the limit to exist, you have to be able to guarantee that you get the same value no matter what direction you approach along. And it's really easy to come up with examples where you get different values, right? So in this first one here, if I go along the x-axis, then I would get the limit as x goes to 0 of just 2x over x, I would get 2, right? If I went along, so that's approaching along the x-axis. If I approach along the y-axis, it becomes the limit as y goes to 0 of, right, so now I'm going to set x equal to 0, and then I have 3y squared over y, and this time the limit is 0, right? So you get different values along different paths, so the limit doesn't exist. The second one, this is kind of either fun or annoying, depending on your point of view. If you approach along y is equal to, if I approach along any straight line, so you might think that it's good enough, we want to check all possible directions, so let's just check every straight line path, so like every right, yeah, so for Hannah's question, I'm not testing you on limits. The main thing you're responsible for several variables is basically partial derivatives and tangent planes. That's what's in the calendar. So that's what we're gonna focus on. But yeah, just to point out this one, you might think that you've covered all your all possibilities if you consider every single straight line path kind of coming into the point. So we're going to consider any possible slope. But you can check. I'm going to leave this as an exercise for you to check. If you put y equal to m times x, the limit will be 0. Okay? But if you go along this curve, if we go along x is equal to y squared, you get a limit of 1/2. Super weird, right? You can plot this one to try to see what's going on. It's really strange. There's kind of this little ridge that tracks that x equals y squared. There's this ridge at height 1/2 along there. And everywhere else it goes to 0, right? So there's kind of like a weird discontinuity going on there. Strange stuff can happen when you're doing limits in several variables, okay? And so those because limits don't behave very well, that causes problems for derivatives. Because the first thought that you might have for generalizing the derivative is say, well, why don't I just do something like, I don't know, what if I did like limit, I don't know, now I have two variables. So maybe there's an h1 and an h2. And those are both going to 0, 0. And then I do like, well, I don't know, x plus h1 and y plus h1 minus f of xy. H2 over here. And then, so you try something like this, and then, well, the first thing that comes up is like, oh, what do I even divide by? What do I put in? What is it? Actually, it turns out later on that one of the things that does make sense is you actually divide by kind of the distance. So h1 squared plus h2 squared, right? How far away is this point from the origin? But this turns out this does not work. This fails. And the main reason it fails is you get different answers along different paths, right? This limit, almost always, this limit will not exist because you get different values along different paths. So this is not the right way to generalize the definition of the derivative. Actually, if you do want to try and understand how to generalize the definition of the derivative, it turns out that there are ways to do it, but this is not it. In fact, the right way to kind of take this and rewrite it in a form that does translate is to say something like, well, this is the same thing as saying the limit as h goes to 0 of f of c plus h minus f of c minus some number that we'll call the derivative times h over h is 0. It turns out you can make some progress if you rewrite the limit like that. But again, this is Calc 3, Calc 4 stuff. This is not This is not something that you worry about in 2565. But there is a way to kind of do it. And it turns out that what really stands in for the derivative is something called the gradient. Actually, well, it's the gradient for real valued functions. But you can also look at vector valued functions of several variables, and you can actually find out that there's a certain matrix. There's a linear transformation that works. And the way you kind of understand this, if you've done linear algebra, I know not everyone has, is you think of the derivative as sort of like the best possible linear approximation. And so if you're thinking about a function that goes between like R3 to R4 or something like that, between different spaces, and you say, well, what should be the best linear approximation to a function? Well, the best linear approximation should be a linear transformation, right? And then linear transformations can be represented by matrices. And it turns out that the matrix you want is like a matrix of partial derivatives. So really, it comes down to understanding how to do partial derivatives. And for now, we kind of decide that we're satisfied with just knowing how to do partial derivatives, and that's, we don't want to get too carried away. So basically what you do is you say, okay, we tried to set up this limit, and it doesn't work because the answer depends on the direction you take, the path along which you sort of let this h approach 0. And so you say, well, why don't we just choose paths, right? Each path that we choose does give us a definite answer. So let's try approaching, in a direction parallel to the x-axis or a direction parallel to the y-axis, and see what we get. And what you get are these partial derivatives. Okay. The other notation that you'll see for them, you'll also see this notation, these kind of curly d's, d, df, dx. At AB, and d, df, dy at AB. So you'll also see that sort of curly notation, the curly d notation for partial derivatives. Okay, so you'll see that. And so the idea here is basically when you're doing the partial derivative with respect to x, right? Notice that we kind of take y as constant, right? We're holding y constant, and we're taking the derivative with respect to x, right? And when you're doing the partial with respect to y, x is constant, right? X has the same value here and here, but y is varying, right? We add the h in on the y. And so we hold x constant, and we take the derivative with respect to y. And it turns out, practically speaking, that's pretty much all you do for partial derivatives. So what we're going to do, before we get to the end of this, we're going to do a few examples just showing you how to compute partial derivatives. We'll talk a little bit about what it means, and then we'll end. Either when I get to the end of the slides or my computer dies, whichever happens first. I hope we do better than we did last time. Okay, so here's an example. So I've got some function. I want to calculate the partial derivative with respect to x at a point. So one of the things I could do is I could just use the limit definition. I could say, all right, well, the partial derivative with respect to x at the point 1, 2 is going to be the limit h going to 0 of f of 1 plus h 2 minus f at 1, 2 over h. And so I come up here and I say, okay, so what is at 1 plus h and 2? What do I get? I get 1 plus h squared times 2, 3 times 1 plus h plus 2. So that is going to be 2 plus 4h plus 2h squared plus 3 plus 3h plus 2. I'm going to clean that up down here. So I have 2h squared plus 7h, okay, plus 2 plus 3 plus 2, plus 7. On the other hand, f of 1, 2, if I just put x equal to 1, y equal to 2, I'm going to get 2 plus 3 plus 2, I get 7 over h, right? So I get the limit, h going to 0, 2h squared plus 7h over h. So that's the limit, h going to 0, of 2h plus 7. Okay, so I get 7 for my answer. Fine. Or the other thing I could do is I could say, well, look, why don't I just calculate what is f of x2? Y equal to 2. Okay, so f of x2 would be 2x squared plus 3x plus 2. So that's a function of x only, right? I'm holding y constant at 2, so now I just have a function of x. So let's call that g of x. So then g prime of x would be 4x plus 3. So g prime of 1 would be 4 times 1 plus 3, which is 7. And of course, option 2 is easier, right? And that's the point. And now the point is that we can start doing this where we're not even necessarily putting in x equals 1 or a y equals 2 when we're doing the derivative, right? If I want to calculate in general, what is the partial derivative with respect to x for at a general point xy, well, what I do is I come up to my function and I say, okay, I want to take the derivative with respect to x, and if I'm doing the x derivative, I treat y as a constant, right? So in that x squared times y, I'm just treating y as a constant. If I'm treating y as a constant, then that's just like a constant times x squared. So if I'm taking the derivative of a constant times x squared, I just get that same constant times 2x. So I would get 2x times the constant times the y, right? And then plus 3. And then similarly, if I wanted to do the partial with respect to y, I would treat x as a constant and I would take the derivative with respect to y. And if I did that, well, if x is a constant, then these terms go away when I take the y derivative, right? They're constants as far as y is concerned. So the derivative is 0. And then here, well, the derivative of y is just 1 times a constant, times this x squared, right? So I just get x squared. So that's the right way to do partial derivatives. It takes practice. You've got time to practice. One of the things we get lucky on is our exam is right near the tail end of the exam period. You've got over a week to play with this stuff and get the hang of it, okay? Which is kind of nice. All right, let's do a couple more examples. So for this first one, right, when I want to take the x derivative, again, if I'm taking the derivative with respect to x, I just focus on taking the derivative of the x part. And one of the things that actually might help me is to say, well, you know what, this e to the 2x plus 2x plus 3y, I could always do it like that, right? Laws of exponents still work even if you have more than one variable. Okay? And so if I'm taking the partial derivative with respect to x, well, in that first term, derivative of x squared is 2x, and I just multiply by y cubed because I just treat that as a constant. Okay? The derivative of e to the 2x is 2e to the 2x, and then I'm multiplying by e to the 3y. Okay? And actually, even, let me just put it on the side, even if I did the partial with respect to x of e to the 2x plus 3y, regular chain rule still applies for partial derivatives. So I can say, well, that is going to be e to the 2x plus 3y, but then I have to multiply by the partial derivative of 2x plus 3y, and I'm doing partial with respect to x, so the x derivative gives me 2. So I can do it like that as well, right? once you've practiced this, you'll be able to do this just as easily as you do it for regular derivatives. Okay. So I'm doing the partial with respect to y. In the first term, the derivative of y cubed is 3y squared, right? I leave the x alone, it's like a constant. So I just get 3y squared times x squared, or maybe I'll write that as 3x squared y squared. And then using the same reasoning as we did here, if I was doing the derivative with respect to y, then the y derivative down here would give me a 3, right? So I would get 3 e to the 2x plus 3y. Okay? All right. If I'm doing that second one, I want to do the partial derivative with respect to x of x squared sine y over x squared plus y squared. Well, you still end up doing basically quotient rule here, right? Derivative of the top, derivative of x squared is 2x, and we just leave sine y alone because it's a function of y. So derivative of the top times the bottom minus the top times the derivative of the bottom with respect to x, just 2x, divided by the bottom squared, right? And quotient rule is just as ugly in two variables as it is in one variable. Okay, and if I wanted to do the partial with respect to y, it's going to be the same kind of story. Derivative of the top. Now I'm doing the derivative with respect to y, so I leave the x squared alone. It only depends on x. I take the derivative of sine y, and I get cos y. So I get x squared cos y. That's the derivative of the top times the bottom minus the top times the derivative of the bottom, but this time with respect to y. So the derivative of x squared plus y squared with respect to y gives me 2y this time. And then divide by the bottom squared. Okay. Same kind of idea. All right. Let me erase this stuff here so we can do that last example. Okay. All right. Example 3. Now, before I proceed, I want to do one thing. If you do this, you will make your life so much easier. Distribute that square root across the two terms. X to the 1/2, y to the 3/2, plus tan of x squared y. Okay? So if I do that, then for the x derivative, I just need power rule for that first term, right? I get 1/2 x to the minus 1/2 y to the 3/2, right? I just leave the y part alone. Oh, that's x squared times y. And now for the other one, I do kind of standard chain rule, right? Derivative of tangent first. Derivative of tan gives me secant squared x squared y. But then I have to multiply by the derivative of the inside. And I'm doing the derivative with respect to x. So the x derivative of x squared y, x derivative of x squared is 2x. So it's 2x times y. Okay. For the y derivative, now I'm going to take the derivative of y to the 3/2, right? So I get 3/2 x to the 1/2, y to the, so 3/2 minus 1 leaves me with y to the 1/2. And then on the second term, again, I have to take the derivative of tangent, so I get secant squared x squared y. This time I take the derivative of the inside with respect to y. So derivative of x squared times y with respect to y is just x squared, right? Because the derivative of y is just 1. So I get that extra x squared on the outside. I'll put some extra parentheses there, make sure it's clear that that's not part of the secant function. Okay. Doable. Hopefully that's doable. I think most of you can handle it. It's not so bad. One thing I want to point out is that if you didn't do, for example, if you left that square root alone, you did like x, y cubed, and you leave it as the square root, well then you have to do like 1/2 times xy cubed to the minus 1/2, and then you have to do the derivative of the xy cubed, and so then you get, it's this is not, you can still do it that way. It's just annoying. It's much easier to just, if you have roots like that, it's easier to sort of use laws of exponents to simplify first, if you can, right? Keeping in mind that if you had, if I had square root of a sum, like if there was imagine there was a square root here, right? If there's a sum under the square root, there's not much you can do about it. You gotta deal with the square root, right? Because square roots don't distribute across sums, but they do distribute across products. So sometimes that can simplify things for you. Just make sure you're not breaking laws of algebra when you simplify. All right, how are we doing? Doing okay? So, next thing I want to mention is you can, once you've done one partial derivative, you can do another, right? But you get actually a little bit more excitement with two variables because, if you have one variable, you take the derivative once. Okay, now you have f prime, you take it again, you get f double prime. Fine, that's kind of all you do. But if you've got two variables, now you can mix and match, right? Because you take the derivative first with respect to x. Well, what's your second derivative going to be? Is it going to be still another derivative with respect to x, or are you going to do the derivative with respect to y, right? So if you do the derivative with respect to x, and then you do the derivative with respect to x again, right? Well, then you've done two derivatives with respect to x. And so we might write that like this. fxx means take the derivative twice with respect to x. But the other thing you could do is you could take the derivative once with respect to x, and then with respect to y. Okay? And we might write it this way. So either d squared y dy dx or f sub xy, right? So you could do x and then y. You could also do y and then x, and that gives you fyx, which we can also write like that using that kind of Leibniz notation, right? Or you could do the derivative twice with respect to y. So there are 4 different second order partial derivatives, right? Whereas there's only 1 if you're in one variable. Now you get 4. If you're doing 3 variables, there are 9 different second order partials that you can consider, right? Because you can do xx, xy, xz, yz, zy, yy. There's lots of possibilities there, right? But usually it's not quite as many as you think, because almost always those mixed derivatives, these ones in the middle, these ones here, they usually come out to be the same. And this is a theorem. There's a theorem called Clairaut's theorem, which says that as long as all those partial derivatives are continuous, and again, you define continuity for several variables the same way you do for one variable, it's just that limits are harder, right? But as long as all the partials are continuous, then those mixed derivatives should be the same, right? And that means, so one of the things that people sometimes get a little bit worked up about is, oh, xy, yx, does this mean do x and then y, or does it mean y and then x, right? You get worried about the notation. There's a good rule of thumb for that. Whichever variable is closest to the function, that's the one that happens first. So this would say do x and then y. And similarly, using this notation, x is closer to f, so you do x and then y. So there are ways of remembering that. But if you get the order mixed up, it usually doesn't matter because these come out to be the same. They're equal for most reasonably well-behaved functions. If you're in kind of a more advanced calculus course, maybe you see some examples where the second order derivatives are not equal, but yet you have to work pretty hard to come up with examples, right? Because most of the functions we work with have continuous derivatives. And so you gotta, mess around with piecewise things. It gets ugly. Keep it simple. Yeah. Okay. So let's do another example. Yeah, we've got 20 minutes. Computer's still working. Let's do some second order partial derivatives. Okay. I'll do the first one. I'm going to leave the second one for an exercise, but let me walk you through the first one. So for that first one, if I'm doing the partial derivative, first derivative with respect to x, okay, better do the first derivative before we can get the second. So derivative of x to the 4, 4x cubed times cos of x cubed e to the y. But be careful because there's an x cubed inside as well. So you got to use product rule, right? There's a product there. There's a product of two functions. They both have x's in them. So product rule is still going to apply. Okay, so we have x to the 4 times the derivative of cosine is negative sine x cubed times e to the y. And then you still have to multiply by the derivative of the inside. Chain rule also still applies. But partial with respect to x means we ignore the e to the y. We just take the derivative of x cubed, 3x squared. 3x squared e to the y. Let's clean that up. So we have 4x cubed cos of x cubed e to the y minus 3x to the 6 e to the y sine of x cubed. Okay. The y derivative is a little bit easier. We just get minus x to the 4 sine of x cubed e to the y times the partial with respect to y of the inside here, which is going to be x cubed e to the y. So we get minus x to the 7 e to the y sine of, oh, I lost it. Sorry, there's still an e to the y up there. And then sine of x cubed e to the y. Okay, so there's the first order derivatives. Oh, Hannah's telling me I forgot the e to the y, but I remembered it. Thank you, though. Thank you, because I might have forgotten that. Okay, and now we can do the second order, right? So we could do, for example, you know what? Let me give you this one as an exercise, because it's going to be messy, right? Taking the second order, like taking the x derivative twice, means I got to take the derivative with respect to x of that. And both of those terms are going to involve product rule. It's going to be a mess. Yeah. We got better things to do. Oh, if we have time at the end, I'll come back. We got 17 minutes. Let's see. Let me do this one. fxy. So that's the derivative with respect to y of 4x cubed cos of x cubed e to the y minus 3x to the 6th e to the y sine of x cubed e to the y. Okay, still going to get ugly. 12x squared cos of x cubed e to the y. I'm doing product rule on the first one. I'm doing x derivatives, remember. Minus 4x cubed sine. That minus sign comes because the derivative of cos is negative sine. And then e to the y. And then I got to multiply by the derivative of the inside. X derivative of the inside, so 3x squared e to the y. Okay. Oh, but then I also have to take the x derivative, or sorry, the y derivative. Hang on. Sorry, everyone. I'm doing the x derivative again, and I told you I was going to do the y derivative. Let's get it right. Somebody's going to correct me on that, and then the delay is going to catch up with us again. Okay, y derivative. Sorry. If I'm taking the y derivative of this part, I'm going to get minus 4x cubed sine of x cubed e to the y, and now I take the y derivative of the inside, which is just x cubed e to the y. Okay, here I do have to do product rule, right? So I'm going to get minus 3x to the 6 e to the y. Derivative of e to the y is e to the y. Alright, so in this term, I'm doing the derivative of that part. And then I have to do minus 3x to the 6th e to the y. Now I take the derivative of sine, I get cosine, and then I multiply by the derivative of the inside with respect to y. I get x cubed e to the y. We're going to need another page here. Okay. All right. It's a mess, right? We can probably clean it up a little bit. I can still see because of the display lag. I can get this going on over here. Okay, so my fxy ends up being, there we go. I already changed the page. Okay, x cubed e to the y. Oops. I wasn't fast enough. So there were two terms that had x cubed e to the y in them, right? There was this one and this one. So there's, and actually let's pull up the minus sign as well because we have minus in both. Okay, and then we've got 4x cubed okay, cosine of x cubed e to the y. Okay, and then the other one was, or sorry, that one's sine, and then it's x to the 6th e to the y. Okay. Okay, x to the 6th e to the y, cos x cubed y. And we had one more term, right? I was missing a 3 there. 3x to the 6th e to the y. Got it. 3 there. And okay. So yeah, it gets ugly, right? It gets ugly in a hurry. Make sure I got that all right. I did. Okay. X to 7 e to the y. Now let me do the other one. So remember that we had x to the 7 e to the y. Cosine of x cubed e to the y, right? That was the y derivative. So now let's try this one, fyx. After this, I'm moving on, right? Yeah, there's two other mixed partials, but like it's awful. It's really awful. So now what I'm going to do is I'm going to do the x derivative of this. So let's see, what do we get? Minus 7x to the 6 e to the y cosine of x cubed e to the y. Okay. Wait, is it cos? Sine. Sorry. It's hard when you don't have the whole everything there in front of you. And so that's we took the derivative of this part. That's the first bit of the product rule. And now we got to deal with that part. So we're going to get minus x to the 7 e to the y cosine of x cubed e to the y. And we multiply by the derivative of the inside, which is 3x squared e to the y. So let me see. What do I have? I have sine of x cubed e to the y times minus 7x to the 6 e to the y plus cosine x cubed e to the y times minus 3x to the 9 e to the y times e to the y, so e to the 2y. So I get it cleaned up to there. And then we might wonder, like, okay, what about what we had up here? Did that work? If we clean this one up, do I get the same thing? Sine x cubed e to the y. Okay. I'm worried that I've got different answers, but let's see. I have, for sine, there's a 3 there. Oh, there's a negative. I'm missing a negative somewhere. Yeah, that should be minus, I think. Because I should have, there's a minus 3x to the 6 e to the y there, and then there is a minus 4 x cubed times x cubed is x to the 6. So I actually get minus 7 x to the 6 e to the y, and then the cos x cubed y. I'm going to get, so there's a 3x to the 6 times x cubed. I get minus 3x to the 9 e to the y times e to the y is e to the 2y. And it does work out. Okay. It's brutal, but we got there, right? Now, other than being an exercise in sort of computational stamina, there's not a lot that we do in 2565 with these second order partial derivatives. We're just kind of introducing that they're a thing. If you go on and you're doing calculus in several variables, you can start doing more with this. So you can start doing, like finding critical points, classifying critical points, just like you do in one variable, like finding, is this critical point a local max or a local min or none of the above? And you can do that. It turns out the second derivative test is a lot more complicated in two variables. One of the reasons why the second derivative test is a lot more complicated is that you could have a local max, right, like this, where kind of you look at this second order partials with respect to x and y, and they're both negative. It's kind of concave down in every direction, so you get a maximum. You could have a minimum where you're concave up in every direction, okay? But you can also have these saddle points where you're concave down in one direction, but you're concave up in another direction, right? And so second derivative tests classifying critical points is a lot harder in several variables. But that's, that's a problem for another class. It's not a 2565 problem. Okay? All right, 6 minutes to go. It's enough time for me to tell you about tangent planes. Okay? I feel like I lost a page. Yes. Sorry about that. So we come to this question of, like, what are you actually computing when you find a partial derivative? Okay? So let's think about the following. Imagine you've got some surface here in space, right? And so this is the graph. Z equals f of xy, okay? And we choose some point in the plane, AB, corresponding point on the surface, right? So up here, this is the point A, B, f of AB. And I guess technically this point down here we should write as a, b, 0 if it's a point in R3. So one of the things we can do is we can say, well, what would happen if I held y constant and I vary x? Okay. So I look at this line. So this would be the line, where y is equal to b, z is equal to 0, and x is, well, x is like free. X is x, right? X is allowed to vary, right? So that line, all the points along that line, there are corresponding points on the surface, right? We just, every point along that line, we plug the x and y coordinates in, we plug xb into the function, we get a spot on the surface, right? Well, if we ignore for a second, we ignore that we're in 3 dimensions. If we just kind of focused on, we have this sort of plane here, right? We have this bit here. And we just kind of focus on that slice where we're in that plane parallel to the xz plane. And you just look at that as now a curve in a plane. Well, it would make sense to ask about, well, what's the tangent to that curve, right? We could talk about this tangent here, lying in that plane, right? We could ask, what is the slope of that line, right? Well, that line there is a line through the point A, B, f of AB. And what I can tell you about that line is that y equals b is constant, right? And z, well, z is going to be basically f of AB plus the slope. And the slope is that x partial derivative. So we get something that looks like that, right? We get like the equation of a tangent line, but it's in the xz plane. And then you could similarly go this way, right? We could consider this line here, and this would be the line where x is equal to a, z is equal to 0, and y, y is y. Y is allowed to vary. And so that is going to correspond to another curve on the surface going that way. And so if I think about that as something sitting in this plane here, this kind of parallel to the xz plane, I can think about the slope of the tangent line to that curve, right? I can think about that tangent there. And, well, that line passes through the same point, but this time what I'm going to have is that x equals a is constant, and z will be, well, that initial point, f of a, b, and this time the slope is now the partial with respect to y minus b. So you can play around, you can check that this works out, right? So those partial derivatives, they sort of give you, imagine you're standing on a hill, right? And you turn in one direction and you start walking. So one of the partial derivatives is going to give you sort of the slope as you start walking in one direction. The other partial derivative, if you turn by 90 degrees and you start walking, gives you the slope in the other direction, right? So you kind of get those two different slopes. The two, you walk parallel to the x-axis or you walk parallel to the y-axis, and you get the two different slopes. That's what the partial derivatives are giving you. Now, the next thing we can do is we can actually sort of combine these two together. Okay? Write down the equation of the plane that contains both lines, right? So this one up here is where you sort of set y equal to b, right? Y is held constant at b, which makes this part 0, right? So if y is equal to b, then this is missing. If x is equal to a, then this is missing. If we allow x and y to both vary, we include both terms, and we get a tangent plane. Okay, so we get a plane, right? And that plane has an equation that looks like this, right? It should remind you of, and what you want to compare to, think about the equation of a tangent line in one variable, right? Y is equal to f of a plus f prime of a times x minus a. It's the same idea, it's just that now you have two variables, and so you have to include one partial derivative for each variable, okay? But you can get this idea of a plane, right? And you can sort of see the plane in that picture, right? We have this plane sitting here. And that plane is sort of the best linear approximation, if you like, to the surface at that point, right? It's the, if you want a flat surface that approximates your graph, it's given by the tangent plane, right? So you always have this idea, you know, it's this standard theme in calculus that something might locally look flat, but globally might be curved, right? Just like the Earth locally looks flat, but globally is curved, despite what some people might say. Okay, so we'll end. Oh, I'm 1 minute over. Let me, you know what the hell? Let's squeeze it in. Okay. Let's say we want to find the equation of a tangent plane to a surface at a point. Let's do it. Let's get her done. Okay. So my function is x squared y. I'm not going to try to graph this. I have no idea what the graph looks like. But there's my function. Okay. Here's my partial with respect to x. 2xy e to the x squared minus y squared, and I get another term. Derivative, so now I got to take the derivative of the exponential, right? So when I take the derivative of this part, I'm going to get the exponential again, and then the derivative of the exponent is 2x. So 2x times that x squared y, I get 2x cubed y e to the x squared minus y squared. The y derivative is going to be x squared e to the x squared minus y squared. This time when I take the derivative of the exponent, I get minus 2y. So I get minus 2x squared y squared e to the x squared minus y squared. So f at minus 1, 1, right? So the minus 1, 1 are this minus 1, 1. That's the x and the y coordinates. So let's just check that we do actually get, we get minus 1 squared times 1, so that's 1. E to the 1 minus 1, e to the 0 is 1. So we do get 1. Okay, so that checks out. This 1 matches that 1. The x derivative at minus 1, 1 is going to be minus 2 minus 2 more. I get minus 4. The exponential part is just going to be 1, so I'm just looking at these numbers out front, right? Both odd powers of x, so I'm going to get minus 1, and then we multiply by the 2's. The y derivative at minus 1, 1 is going to be 1 minus 2 is minus 1. So my tangent plane looks like this. Right, so it's going to be f at minus 1, 1 plus the x derivative at minus 1, 1 times x subtract minus 1, y derivative at minus 1, 1 times y minus 1. So it looks like 1 minus 4 times x plus 1 minus 1 times y minus 1. Okay. We found a tangent plane. That means we're done the course. That's the last thing that we needed to know how to do. Yeah. We made it. Okay. So we're at the end of the material. I put the... so the videos for this material are not embedded in the textbook, but I do have a playlist on YouTube covering multivariable calculus that I did for Math 2580. I did for Calc 4. So there are videos covering this material. I put the link to that playlist on our Moodle page, so you can go have a look. Yeah, I think that's about all we need to do. I'll be in touch, right? You can get me on Piazza, and oh, I might have a mistake. Shouldn't second part of x2x squared y? Maybe. Second part should be Uh, uh, so it is x cubed. Yeah, sorry, thanks for the question. The x cubed comes from the fact that when I take the x derivative of e to the x squared minus y squared, I get e to the x squared minus y squared times 2x, because 2x is the derivative with respect to x of the x squared minus y squared. And then the 2x times the x squared y, 2x times x squared does give me 2x cubed. Okay, you're welcome, everyone. We're not done, of course. There's still the exam to deal with. You still have one tutorial to get in. I have no idea what the hell happened to that quiz that I put on WebWork. Whatever. You don't have to do the quiz. I'm not going to put. If it's not there now, let's just forget about it. Yeah, I don't know where it went. Okay. Keep the questions coming in on the forum, and I'll keep answering them. The last thing I wanted to remind you all about. You can book me on Moodle, right? I put up that booking thing. I'm going to add more appointments in there once I figure out what my week looks like next week. You can book me on Moodle. I put that office hour booking thing there. We can connect for Zoom meetings. So if there's anything that you can't get answered through the forum because you find like you need some actual one-on-one help, book me on that thing. We'll set up Zoom meetings. You can book me more than one person at a time. If 5 of you want to meet to go over something, just set up a meeting. We'll get it done. All right. Okay. Well, you're welcome, everyone. I'm way over my time now. I see I'm 81 minutes into the stream. So I'm gonna end it here. We'll put these slides up on the website for you as well. Thanks for tuning in, and we'll be in touch soon. I'll have more details on that exam coming at you, but probably not until early next week.